You know, we are absolutely surrounded by light every single moment. But what's wild is that all this light, it plays by a very specific, very strict set of rules. And these rules can create some truly bizarre and, well, wonderful effects right in front of our eyes.
I mean, just think about a simple spoon, right? You look into the inside, the part that holds the soup, and boom, your reflection is upside down. Flip it over to the back, and suddenly you're right side up again, just, a little stretched out. What is going on there? It feels like some kind of magic trick, but I promise you, it's pure physics.
And believe it or not, the secret to that spoon and a whole lot more, it all comes down to just two really simple ideas. Two principles that tell us what light does when it hits something. And once you get these two rules, you're going to start seeing the physics hiding in plain sight all around you.
All right, so let's get into it. Let's break down these two fundamental rules. To really get how light creates these reflections and illusions, we first need a really simple way to picture how it's moving through the world. Okay, so physicists have this brilliant little shortcut called the ray model of light. All you have to do is imagine that every light source, the sun, a lamp, even the screen you're looking at right now, is just shooting out these countless, perfectly straight lines of light. We call them rays. And these rays just keep going, straight as an arrow, until they smack into something.
So when one of these rays hits an object, it basically has two choices. Choice 1, it can reflect, just bounce off. Or choice 2, it can refract, which means it goes through the object, but it gets bent as it does. That's it, bouncing or bending. These two simple things are behind everything from your reflection in a mirror to a desert mirage.
So let's start with reflection, the bounce, and use it to finally solve that mystery of the spoon once and for all.
Okay, think about a normal flat mirror, like the one in your bathroom. Things are pretty simple here. Light rays from your face shoot out, they hit the mirror, and they bounce off in this perfectly predictable way. See, the angle they come in at is the exact same angle they leave at. Your brain then traces these bounced rays back to a point that looks like it's behind the mirror, and that's where you see yourself.
Now, there's a cool physics term for this. It's called a virtual image. And it's virtual because the light isn't actually coming from behind the mirror. It only looks like it is. There's no tiny version of you back there. It's just a really convincing optical illusion that your brain creates to make sense of all those perfectly reflected rays.
Right, but that's a flat surface. What happens when the surface isn't flat? Well, the inside of a spoon is what we call a concave mirror. It curves inward. And that one simple curve, it changes absolutely everything about how those light rays bounce.
Now, the rules of reflection are exactly the same, but that curve forces the rays to meet up at a totally new spot. And to figure out where, we can trace three special key rays. First, a ray that comes in straight reflects and passes through a special spot called the focal point. Second, a ray that goes through that focal point first will hit the mirror and reflect back perfectly straight. And third, a ray that hits the mirror dead on just reflects straight back along its own path.
And here it is, the aha moment. When you trace where those three bouncing rays actually cross, they don't meet behind the mirror like before. They meet in front of it. And, this is the key, they cross over, upside down. The rays from the top of your head end up on the bottom, and the rays from your chin end up on top. Your brain sees this crisscrossed image, and that is why you look inverted in a spoon. Boom, mystery solved. So that's reflection, that's the bounce. But remember, light had another choice, bending, or, as physicists call it, refraction. And this is where our perception of reality can get even stranger.
I'm sure you've seen this. You're looking into a swimming pool, and you can see the bottom, but it just never looks quite as deep as it really is, does it? Well, your eyes are being tricked again, but this time, it's not by light bouncing, it's by light bending.
So why does this happen? It's all because light actually changes speed. It travels fastest in a vacuum, a little slower through the air, and even slower when it has to push its way through water. And this change in speed forces the light ray to bend. Scientists have a way to measure this called the index of refraction. It's basically just a number that tells you exactly how much a material is going to bend light.
So, let's picture it. The light rays bouncing off the pool floor travel up through the water in a straight line. But the moment they hit the surface and escape into the air, they speed up, and that causes them to bend. Now, your brain doesn't know this. It always assumes light travels in a perfectly straight line. So it traces those bent rays back and creates a virtual image of the pool bottom that's way higher up than the real thing.
Now, being able to control how light bends isn't just for making pools look shallow. I mean, by mastering this one principle, we have created some of the most important technologies that our entire modern world runs on.
So check this out. What if you could bend light so much that it actually gets trapped inside whatever it's in? Well, you can. If a ray of light that's inside glass or water hits the edge at a really shallow angle, what's known as the critical angle, it literally can't get out. Instead of bending its way out, it reflects back inside. It's trapped. This incredible phenomenon is called total internal reflection.
And this exact principle, this idea of trapping light inside a material, well, it's the engine that powers our entire global internet. It is the secret behind every single fiber optic cable buried under our feet and under the oceans.
Here's how it works. It's pretty genius. Engineers make these incredibly thin, incredibly pure strands of glass fiber. They then shoot pulses of light, which represent our data, our emails, this stream, into one end. Because the fiber is so narrow, the light inside is always hitting the inner wall at an angle that's shallower than that critical angle. So the light just can't escape. It's perfectly trapped, bouncing and reflecting its way down the cable for thousands and thousands of miles.
And the really crucial part here is that because the light is so perfectly trapped, the signal can travel for enormous distances with almost zero loss of information. It is, by far, the most efficient way we have to move massive amounts of data from one continent to another, and it does it quite literally at the speed of light.
So there you have it. How crazy is that? From the simple, everyday curiosity of an upside-down reflection in your kitchen, all the way to the fiber optic cables that weave our world together. It all comes down to light's two simple choices. It can bounce, or it can bend. And it just makes you wonder, as we get even better at controlling these two simple rules, what other amazing things will we be able to build?